Hey Tim, let's look at differentiating trigonometrical functions. Here's a useful inequality that we can develop. If you look at this shape, we've got a triangle and an arc over here. So the triangle's at the center of a circle, and then there's an outer triangle with the height here as a tangent to the circle. If we look at the areas of each of these shapes, if we take the first shape, a half AB sine theta is equal to the area of a triangle. Okay, so half r squared sine theta there. A and B are just r. Then if we look at the sector, it's given by half r squared theta, which we're quite familiar with. And then finally, the outer triangle is a half base times height. So half times r, and then the height divided by r is tan theta. So height equals r tan theta. And we've got him over there. So if we multiply this out, we end up with, and divide by half r squared, because each one of them's got a half r squared. See that? Okay, and then we have sine theta is smaller than theta, which is smaller than tan theta. And this only works for theta between 0 and 90 degrees. So that's a useful inequality, and it's used for proving differentiation of cos and sine. If we now look at on the left-hand side, we see that sine theta is smaller than theta. And if we divide by theta, we have sine theta over theta is smaller than 1. And if we look at the right-hand side, okay, we have theta is smaller than tan theta, which is sine over cos. Now if we multiply by cos and divide by theta, we end up with cos theta is smaller than sine theta over theta. And we said that's also smaller than 1. So it's just a little bit of playing around with the inequality and shapes, and this type of thing is used to build up the proof for the differentiation of cos and sine. But I'm not going to go into the proof of that. We're going to jump right in with differentiating sine and cos. If we look at this sine graph, there's a simple little sine x over here. You can see how it starts at 0 and goes up to 1 over there at 90 degrees. And if you look at the cos, he starts at 1 and goes down to 0 and carries on. Now, if we look at the slope here of the sine of x, you can see that m equals 1 when he starts off. And that is equal to cos of x. Then, as he gets to the 90 degrees, you'll see that m is equal to 0, which is also equal to cos of x. Because at 90 degrees, cos of x is 0. So you can see how as the one grows, the other one diminishes. And so the differential of sine is actually cos. Now you'd think, well, if the differential of sine is cos, then surely the differential of cos is sine. But that's not quite the case. Because if you look at the cos graph, we see here at x equals 0, m equals 0, which, yes, you could say it's equal to sine of x. But over here, at 90 degrees, m equals minus 1. Okay, it's backward facing, so it's a negative slope. But that doesn't tie up with sine of x, because sine of x is 1. Okay, so it is equal to minus sine of x. And so we could have reversed this one too, because sine of 0 is plus or minus 0. It doesn't matter. The sign doesn't matter. So we see how differentiating cos is actually minus sine. Differentiating sine is cos. And it comes back to, you know, when you were a kid, you are a kid, but your dad would say, hey, look at the waves on the sea. It's a sine wave. Nobody says, oh, look, there's a cosine wave. So it's always good to remember sine and cos as sine as the benchmark. Sine is the kind of the main guy, and cos is his second cousin. So cos is always unhappy. Cos is always negative, just about 99% of the time. So if you differentiate sine, you get cos. If you differentiate cos, you get minus sine. Okay, it's always a little bit otherwise. But other than that, it's pretty straightforward. Yeah, I just wanted to explain this whole thing with sine and then differentiating to cos. Sine, differentiate to cos. Differentiate again, you get minus sine. And differentiate again, you get minus cos. And so it goes back to sine again. What is really going on here? Sine and cos are 90 degrees out of phase. So the differential of the one is 90 degrees backwards, and then the differential of that one is 90 degrees back. So you get this quadrature as it goes round in a circle. And that it's not just a 180-degree cycle, it's a 90-degree cycle. I hope that helps to understand the difference there. So let's do a couple of examples. Okay, first one, y equals sine of 3x minus pi by 4. Well, based on what we learned previously about differentiation, we can call what's in the bracket u. Okay, and we use the chain rule. So if you differentiate sine, he goes to cos, the u remains just as he is, and then we differentiate u, and we see, okay, differential of that is just 3, so we times by 3. So the chain rule works just as well with sine and cos as it did with polynomials and each of the x's. Here's another very difficult example. Okay, y equals cos to the 4 of 3x squared plus 2x. You'll see how simply it reduces. So first of all, we've got a cos to the 4. Okay, so we're going to say it's like u to the 4. If we differentiate u to the 4, we bring the 4 down to the front, and we keep u just as he is, but now he's to the 3. So that's the first part done. Now we must differentiate the cos of 3x squared plus 2x. So we've got another u now. We've got a cos of u. Okay, so we're defining another u. I'm just doing a chain rule within a chain rule. So if we differentiate the cos, we get minus sine of u. Doesn't change. And then finally, we differentiate our u. There's our u. We differentiate him. We get 6x plus 2. Now we can multiply everything out and simplify the terms. Okay, so it's all simple steps, but you must just pay attention to make sure that everything gets differentiated and we don't leave anything out. Here's another example, y equals sec x. Did I teach you anything about differentiating sec x? No. We've learned now about sine and cos. So let's change the sec into cos, okay, because sec x equals 1 over cos x. But we've learned that with powers, it's better to write them as an index. So instead of 1 over cos x, I've written it straight as cos x to the minus 1. Now we know how to differentiate a power to the minus 1. Okay, and our u this time is just cos x. So u to the minus 1 gets differentiated. You bring the minus 1 to the front and becomes cos of x to the minus 2. Okay, that's not quite correctly I've written it there. So it's cos of x to the minus 2. We can take that bracket away. Okay, then we must differentiate the u part, which is cos x. If you differentiate cos x, it's minus sine x. So now we can quickly see that y dash equals sine x, it's over there, the minuses have cancelled, divided by cos squared x. But sine over cos is sec x, sine over cos is tan x, and then 1 over cos is sec x, so that's another way to write it. So this is a useful one to remember. The differential of sec x equals sec x tan x. It actually gets more complicated as you differentiate. Here's another one. Y equals ln of sec x. Okay, now we can remember that the differential of ln, if y equals ln x, y dash equals 1 over x, is the reciprocal. So we let u be sec x, so we've got ln of u, we simply go as 1 over u, 1 over sec x, and now we've just worked out what the differential of sec x is. It's sec x times tan x, so there we go. We just put him down there, and now we multiply them out, the secs cancel, and we're left with tan x. So the differential of ln sec x is tan x. Here's a practical example where the height is given by 6 plus 3 cos pi t over 6. And you're asked to find out when is the tide rising the fastest. You're looking at the rate of rise here, so you can see I'm going to need to differentiate. Notice that this question is not asking you where the min-max is, and that's mostly where questions go on differentiation. In this case, actually want to find out where the maximum of the differential is. So h dash equals, well, the 3 remains, the 6 disappears, 3 in front there remains as he is, and you're differentiating cos, so cos goes to minus sine, and the u remains as pi t over 6, and then we differentiate the u, becomes pi over 6. So that reduces to minus a half sine pi t over 6. So the maximum occurs when the sine pi t over 6 is minus 1. Okay, because it's got the minus in front there, so it's minus times a minus is a plus. The absolute value is maximum is going to be a half, because you know sine is bounded by 1 and minus 1. So the height can never be above a half or below minus a half. So the maximum occurs when this sine term is minus 1, and from there you can say that pi t over 6 equals 3 pi over 2, which is your 270 degrees. You can see how sine is minus 1 there at 270 degrees. Find the min-max of y equals 4 cos x plus 2 cos 2x. We differentiate y dash equals, differentiate cos is minus sine, 4 remains as it is, and you differentiate cos, you get sine of, it becomes sine of 2x, and then you differentiate the u, put that in front, and it becomes 2. So if you want to find the min-max, you have to find where y dash is equal to 0, which is difficult because you've got two different angles. But you must always remember your double angle formula, and then sine 2x reduces to 2 sine x cos x. So y dash equals minus 4 sine x minus 4 sine x cos x, and we set him to equal to 0. And we can factorize, we can take out the common sine x there. So you have minus 4 sine x, 1 plus cos x equals 0. And from there, you can find your min-max by either equating that one equals 0 or that one equals 0. You can find your roots of your equation. Let's look at how to integrate sine and cos now. The integral of cos of x is equal to sine of x plus your constant. Remember, it's an indefinite integral. There's no a from a to b. And then the integral of sine x is minus cos x. So this is the one time when cos x is happy. Hey? There's no negative there. But it's only because he's the inverse of the differential. Because if you differentiate sine, you get cos. So if you integrate cos, you get sine. Remember this. Remember the signs. Remember the integral of sine is negative. It's very easy to make a mistake when you're doing integrals like this. And it's just watch out for it. Okay. So an example is find the integral of sine 2x plus pi by 3. Okay, can you recognize the ax plus b? And the integral of sine is minus cos. You keep the ax plus b as it is, and you times it by 1 over a. And don't forget your constant term. Do you want to get 2 out of 3, or do you want to get 3 out of 3? Here's a very important tip. Integration is always easy. You can do very complicated differentiation using the chain rule, and it's wonderful. You can just differentiate, and you differentiate again, a u within a u within a u, like we saw in the previous example. But fortunately, integration is so complicated that it becomes easy. And so there are no fancy rules. There's no chain rule for integration yet. Later on in university, you might have some rules where you'll pick up things, but for now, integration is easy. What have we learned about what can we do? You must look at what you can do before you attempt the sum. We can integrate powers in x. For example, x to the minus 3. Easy, okay? Polynomials, integrate them, no problem. We can integrate e to the x. Integral of e to the x is e to the x, okay? You can integrate 1 over x. The integral of the reciprocal is ln x. And now we can integrate sine x and cos x. And that's all we can do. The only exception is when we have, instead of an x, we have ax plus b. So now, where you just put 1 over a in front and you integrate it as if it's just a big x. Okay, so integration is easy. It's very important. However, you're going to get given sums to integrate. They look very hard. Now, the problem comes in is when you try and integrate these hard sums. The trick is always to try and simplify them first so that they're in one of these forms here. Okay, so there's no chain rule. You have to keep it simple. And this is where these double angle formulas and a plus b type sums come in handy. For example, let's say I was asked to integrate sine a cos a. I can't, because I've got two functions multiplying each other. It's not just an integral of a cos a, it's not an integral of sine a, it's a combination of the two. So what am I going to do? Well, I must write it as sine 2a. And now it's just of the form sine of a, ax plus b. See there? The 2a, and then b is 0. So it's easy to integrate sine 2a. Similarly, if I have to integrate cos squared a, I can't. Why is that? Because it's a complicated function, cos to the square, and I can't do that. So what must I do? I'm going to expand it using the double angle formula. So I can express the cos squared as simply divide by 2 there. So you get a half plus a half cos 2a, which is easy to integrate. Same with sine squared. So if I'm asked to integrate any of these complex functions, it simply cannot be done. But if I use these other equations that we've learned in the previous chapter, then they reduce quite easily. Here's another one. If you're asked to integrate sine a cos b, just integrate sine of a plus b plus sine of a minus b. Okay, and they're always, so you have to simplify first before trying to integrate. Just a quick summary out of this chapter. What do you need to know? First of all, that sine of theta is smaller than tan theta. And that's for theta between 0 and pi by 2. Then, if y equals sine x, y dash equals cos x. If y equals cos x, y dash equals minus sine x. The integral of cos x is sine x, and the integral of sine x is minus cos x. And don't forget your constant. Always be on the lookout when you're integrating to look for ax plus b, and reduce complex functions to the function of ax plus b, otherwise it can't be done. And you do this by using the addition-subtraction formula, which is actually from a previous chapter, but you use them to substitute in. So thanks very much. That's all from me. If you have any questions or you want some examples, feel free to email me. I'm more than happy to help. Cheerio.